Welcome to the video for section 1.2, and section 1.2 is going to be talking about characteristics of function graphs. So our main goal in this section is going to be, if I give you a graph of a function, can you tell me some characteristics or attributes of that function based on what you see on the graph? Okay, in order to successfully watch this video, make sure you have your textbook in front of you. We're starting on page 17. At certain points of the video, I will have you pause and answer some questions in the book. You also probably want to have a piece of loose leaf paper for notes or your notebook if you're using a spiral notebook, because I am going to give you a lot of definitions that you're probably going to want to pause the video and copy down at various points. So we'll start with a couple basic terms relating to a graph. The first is talking about where a graph is positive. So when we mean by a graph being positive, we mean what x values is the graph above the x-axis. In other words, what values of x get us a y that's going to be positive? Because remember, if you're positive, the positive part of the y-axis, that's above the x-axis. Then obviously, if we're talking about parts of the graph or intervals of the graph that are below the x-axis, we use the phrase negative, because again, at those x values, the function has a negative y. Okay, this is that same graph that's listed on page 17. I'm not going to answer any of the questions that's in the book, because I want you to try them on your own for practice. But, for instance, one example of a positive interval would be right here that I'm circling, because from 5 to 7, the graph is above the x-axis. All of these different function values represented by this triangle are all positive. So we could say that this graph is positive when 5 is less than x, which is less than 7. Notice I didn't put equals here, because when x equals 5, I'm on the x-axis. So I'm not positive, I'm not above it, I'm right on it. Same goes with 7. I'm not above it, I'm right on it. Now, if we want an example of a negative interval, we could say, like right here, from 0 to 1. So I could say the set of all x that 0 is less than or equal to x is less than 1. In interval notation, you would write it with a closed at 0 and an open at 1. Notice why the 0 is closed here, but none of the endpoints in the positive are closed, because when x equals 0, I am below the x-axis, right there at 0, negative 1. Okay, I would pause the video right now and answer questions A and B, just practicing positive and negative. Circle which word is correct for parts A and B. Now we'll move into increasing and decreasing. So here's some terminology for that, and it's a little different than how it's written in the book. So if you're taking notes, as you're taking notes, I would write these definitions. I think they're a little bit clearer. So a function is increasing over an interval if the graph rises from left to right, and I'll show you a picture about that in a second. If a graph falls from left to right, then we say that the function is decreasing over that interval. And here's that same picture we've been working with. So if we want an example of an increasing interval, right here, from 0 to 2, the line segment is increasing from left to right. It's rising. So we can say that this graph is increasing from 0 less than x less than 2, or if you want to use interval notation from the last section, the open interval from 0 to 2. If we want an area where it's decreasing, here's an example of something that's decreasing. And we can say that's happening when 10 is less than x is less than 11, or again, the open interval from 10 to 11, all the values between 10 and 11. As you go from left to right, you have a graph that's falling or decreasing. Okay, now I want you to try a couple other intervals that are listed in questions C and D on the video. So pause the video, give them a try. When you feel like you have an answer, you can move on. Okay, average rate of change is next. It's a fancy phrase for something you talked about in Algebra 1 a lot. The average rate of change for a function is just the slope between the two endpoints of an interval. Okay, and recall that there's your formula for slope. M equals y2 minus y1 over x2 minus x1, rise over run. So let's just do a numeric example of this, different than the one they ask for in the book. So if I asked you, what was the average rate of change over the interval, let's say, 4 is less than or equal to x is less than or equal to 6. Could also have it written in interval notation like this, the open interval or closed interval from 4 to 6. All I'm asking for is what is the slope of the line segment that connects these two dots that I've just circled in red. So in order to get those slopes, we need coordinates. So at 6, y is at 1, so 6 comma 1 is the coordinates of that point. At the left end point here, we're at point 4 comma 1. Excuse me, 4 comma negative 1 because we're below the x-axis. Now we're just going to plug all this information in to our slope formula. So m equals y2, which is the 1 here, minus y1, which is negative 1, over x2, which is 6, minus x1, which is 4. Okay, we'll do the top part first. Double negative. 1 minus negative 1 is the same thing as 1 plus 1, which is 2. 6 minus 4 is also 2. 2 over 2 reduces to 1. Suppose I wanted just to do another one. The average rate of change from, let's say, maybe 7 to 10. Do that right here. Average ROC for rate of change from 7 to 10. Again, I'll get my two coordinates. So when x is 7, y is 0. So this is the point 7 comma 0. When x is 10, y is 1. So this is the point 10 comma 1. We'll plug into our slope formula, y2 minus y1 over x2 minus x1. 1 minus 0 is 1. 10 minus 7 is 3. I can't reduce it anymore. So the average rate of change of this graph from 7 to 10 is 1/3. Okay? Question E in your book on page 17 asks about average rate of change with a different interval. Pause the video now and give that a try. Okay, another interesting area in a graph involves what are known as the extreme values, or the turning points. A turning point is just where the graph changes direction. So if we go back before a few slides ago, we were talking about intervals that are increasing, intervals that are decreasing. If you notice in the graph on page 17, there's certain points where the graph kind of changes direction. You go from increasing and then it drops down to be decreasing as you read it from left to right. That's an example of a turning point. Now, depending on how the graph changes direction, that turning point can be defined a little bit more specifically. If the graph changes from increasing to decreasing, then the y-coordinate, or the value of f of x, where that graph changes, let me underline that. When I talk about value of f of x, I'm talking about the y value. We call that a maximum of the function. Likewise, when a graph changes from decreasing to increasing, we call that y value the maximum. Notice, this is very different than all the other characteristics we've looked at so far in this video. So far, everything we've done is we've talked about the x-coordinates, or intervals of x values. Now we're going to look specifically at the y's. Okay? So if we look at this graph again, I'll just pick one turning point right here. At x equals 10, the graph changes from being increasing and then goes to decreasing. So since we're changing from increasing to decreasing, we call this point not just a turning point, but a maximum. And when we go to describe it, we're going to use its y-coordinate. So if I pen across here to the y-axis, I see that this point has a y-coordinate of 1. So that means this function has a maximum at 1. The graph only rises as high as y equals 1, and then it turns around and starts to fall backwards again and goes down closer to the x-axis. That's what we mean by turning points. That's what we mean by increasing and decreasing and max and min. I'll give you an example of a minimum right here. Okay? The graph starts by decreasing down to -1 on the y-axis, and then changes direction up here and goes pointing back upward and increases. So since we went from decreasing to increasing, we can call this dot a minimum. And we can say the function has a minimum value at -1, because that's the y-coordinate of that point. Okay? F, G, H, and I now are going to ask you a little more specific questions about turning points to see if you get the idea of the definition. So why don't you pause the video and give those a try. All right, now we're down to our last and final characteristic that we're going to be studying in this section, and that is zeros. A zero of a function is where the graph intersects with the x-axis. This is also known as an x-intercept. You may have heard that term before in Algebra 1. I know we did a little bit of it at the beginning of the year. Zeros, x-intercepts, they all mean the same thing. It's where the graph intersects the x-axis. Another way to define it, and the reason why it gets the name zero, is because the y value, f of x, equals 0 at these points. Case in point, here's an example right here. This is the point 3, 0, because y equals 0 at this point. This is also a point where the graph crosses the x-axis. So we can say that this function has a 0 at x equals 3. It's not the only place it has a 0. Functions can have more than one 0, but this is one example of it. We're going to talk a lot about zeros this year because as we start solving more complicated equations and we try to graph functions, in order to find places where the graph hits the x-axis, we're going to have to solve equations equal to 0. Okay, so this is a term that we're going to use a lot as the year progresses, so please understand it. When I talk about zeros, when I say x-intercept, I'm talking about the exact same thing when I'm talking about a function. All right, we've gone through now all the terminology you need to know. Please answer questions J and K from page 18 of your book. We'll go over all these answers in class tomorrow, as well as answer any questions you have. We'll additionally do some more practice with this. Thank you for watching the video. If you have any further questions, please be sure to ask me.